Welcome everyone to the 7th Science Hour, but the first one for this year. Nikki Gruber and myself has the honor to host this Science Hour, so it was organized and then we're hosting it from Work Package 5. And I know it will be sort of like a rotation between the assessment work packages, so Work Package 6, 7, and 8 for each month, and I think it's at least slated for 2 rotations, if I'm not mistaken. So yeah, this time around, the science hours would focus very much on the sciences pertaining to EERIE, and we're hoping to generate a lot of discussions with it. Just a little bit, possibly we all already know that EERIE's main scientific goal is to address the role of mesoscale eddies on the climate system. And then briefly, we categorize the assessment of packages to eddy impacts on like local RC coupling, which is what package 5, on the ocean, what package 6, on the atmosphere, what package 7, and on regional climate variability and extremes for what package 8. So since today it's hosted by what package 5, we will sort of focus a little bit more on representation of mesoscale ocean eddies, as well as their impact on RC interactions. But really, we hope to have a lot of cross-work package like discussions. So Malcolm and I are going to share some collective works from Work Package 5. So, I mean, even though it says Work Package 5, I mean, seriously, the work packages are just more for organizational categorizations. But science itself knows no boundaries. So, you know, please, let's have the scientific discussion. Yes, Nikki, I stole it from you. Sorry about that. Yeah, so as I said, Malcolm and I would share some collective works for looking into mesoscale RC coupling from both an Eulerian and a Lagrangian view. And we really hope that we'll have some lively discussions over it. I guess I can... I'm sorry, I was starting all this, and then I forgot to mention a little bit of an announcement before I start the presentations. And Thomas reminded us with regards to upcoming events. So one really upcoming one led by Anne-Marie is the joint session between EERIE and Medley, if I'm not mistaken, in Grenoble. So on the 1st of February, Malcolm will be giving a talk. I'm assuming there is a hybrid option for people's attendance. Yeah. Fantastic.
Yeah, I have not sent the link yet, but I will send it probably Monday or something. I will send a link. I will post it on Mattermost. And I also would like to draw your attention to the talk after Malcolm by Thierry Penduf. Thierry has worked on how eddies create large scale, long time scale, typically interannual, 2 years and more variability in the ocean from forced simulations. So like he has the ensemble of 50 different simulations of the ocean forced by the atmosphere, by exactly the same atmosphere, and he looks at the spread in the ensemble and so on. So I think this point of view, which is quite different from the point of view of a coupled model, may be interesting to many of you. And it's also very interesting to Thierry. I mean, he will be really happy to have questions or ideas from people from the coupled ocean atmosphere modeling community as to, I mean, what is most relevant in his results for this community. So that should be interesting. And I'll send the link and people can join anytime.
Fantastic. I think Thomas also sent out on the chat the web link to a lot of upcoming events. So we have the joint EERIE medley session on 1st of February, and I believe the next science hour is on February 22nd. It will be presented by Nico. That will be it's also really interesting because it's on the impact of eddies or model resolution for deep water formation and links to AMOC. As well as the upcoming hackathon from March 4th to 8th, which will be held here in Hamburg, just so that you guys have it all on your calendars for all these different events coming up. Okay, So I guess I'll start with a presentation and then I'll pass it over to Malcolm. We're doing a tag team, but feel free to ask us questions along the way. We don't want it to be a monologue or just a dialogue between me and Malcolm. It should be with everyone. So yeah, chime in whenever you guys would like to. So I'm gonna, oh dear.
And for chiming in, should we just raise the hand or what do you prefer?
Oh, I won't concentrate on looking at hands. So I guess.
Yeah, I'll try and catch the hands. Yeah.
Okay.
Okay.
I could do that. Shoot, I'm having issues with sharing the screen. I have to quit and reopen. Great. I might have to log out for 1 second and log back in. I'm really sorry, but apparently I can't share my screen yet.
Okay, maybe I can.
That's okay. Malcolm, maybe you want to start.
I'll try and fill in. I'll fill for you
Okay.
by maybe just I can actually find my presentation, my long list of things. Where is it? So hopefully you can see that, and so I can just maybe remind you what the models that we have within EERIE. So we have the Met Office model. We're running CMIP type simulation, so kind of 1850 pre-industrial control, and then spin up pre-industrial control and historic and into the future. And then the 4 other modeling groups are running high-risk MIP type simulations, so kind of 1950 spin up for about 50 years, and then 1950 control, and then historic into future. And then just one thing to note in terms of the resolutions, because I think particularly for the bit that I'm going to talk about, that it is relevant. So for the Met Office model, the highest resolution in the atmosphere is about 20 kilometers, and that's 20 kilometers in mid-latitudes. And the ocean is the Orca 12, so about 8 kilometer grid. So in that model, the atmosphere resolution is kind of considerably coarser than the ocean resolution. Whereas for the other models, the atmospheres are about 10 kilometers. So MPI with ICON and AVI with the IFS are kind of 10, 8 kilometers or so. And then the ocean for the MPI model is about 5 kilometers. For FISM, it's a variable grid, so somewhere between 13 and 4.5 kilometers. And BSC is the same Orca 12 as the Met Office, so it's 8 kilometers. But so you can see for those other 3 models, the atmosphere and ocean resolutions are very similar. Whereas the Met Office model, the atmosphere is kind of more than twice as low, twice the resolution of the ocean. And I think that will be relevant when I talk a bit about some of the eddy statistics that I'll show. Dian, are you back?
Yes, I am. Thank you.
Yep. Ready? Okay. I'll stop sharing.
I want to share. Yeah, you need to share. Can you guys see this?
Yep.
Now on full screen? Cool.
Yep.
Okay. So thanks, Malcolm, for filling in. Now what we have, I'll be talking actually the overarching theme first. So as we know, EERIE is again about addressing the ocean mesoscale eddies on the climate system. And at least for this science hour, well, in general, actually, we want to see how the model represents ocean mesoscale. How do we quantify mesoscale eddy impact, be it on the ocean, on the atmosphere, sea ice, or air-sea coupling, or air-sea ice coupling? What are sort of processes associated with these ocean mesoscale eddies? Do they differ from the large scale? And perhaps from a methodological point of view, how do we extract the impact of mesoscale eddies? So today specifically, we're going to focus more on representation of mesoscale eddies in models, as well as the impact on local air-sea coupling. So first off, I do have to apologize a little bit because for many of you here who has already seen my presentation during the General Assembly of EERIE, there's quite some overlap. So I hope it's not too boring for you guys. But the thing is, I have tried to expand upon what we've been talking about. Particularly looking into how we might be able to disentangle the spatial scales, primarily mesoscales from the large scales, for each of the coupling processes that we might be interested in. So I'm gonna go from the Eulerian point of view and go straight into the scale dependency of RC coupling. This is particularly looking at SST and wind stress, or the magnitude of wind stress, taken from 2 years of daily data and regressing the wind stress against SST. And in general, what you can see is this blue, so this negative relationship between winds and SST, based on just the total fields. But if you do a smoothing, like a spatial smoothing over it, spatial smoothing over it, you can see that the spatial patterns are quite similar. It's mostly negative also, the relationship. But if we look into the high pass fields, so this uses a 3-degree high pass field, we see totally different spatial patterns and different sign of the relationship between wind stress magnitude and SST. So it really begs the question of what type of resolved processes or mesoscale processes are dominant and which ones are dominant on the large scales, such that they would give rise to different spatial patterns of this type of RC coupling. And so the two dynamical processes that we sort of wanted to touch upon again, which is the thermal feedback and the current feedback. And then we'll look into not just as coupling processes, but also the scale dependencies of these coupling. Thermal feedback and current feedback. This is a table from Renault's paper looking into current feedback, which is really very much just how the surface currents directly affects the winds. And the thermal feedback is more on how SST affects winds, be it directly from SSTs to wind stress that we saw or wind speed, or gradients of SSTs on wind curl or wind divergence. Yeah, so if we take a look again, this one, you have, you guys see my pointer? Yeah, I hope. You see on the bottom left, there is this, based on the full fields, again, it's very similar, wind speeds against SST, you have this negative relationship in the tropics, a little bit into the subtropics, and if you apply a 3-degree smoothing, it's a similar pattern. And this, the process related to this could be seen as the waves feedback or the wind evaporation SST feedback, where if you have faster winds, tends to be more evaporation and cooler SSTs, or if it's slower winds, there's less evaporation and therefore warmer SSTs. So the negative relation of like faster winds, cooler SSTs. However, if you look into the high pass filtered data, so this is for boreal summer on the left side and boreal winter. Again, you can see that the relationship is quite different. It's a positive relationship, in particular in the mid-latitudes, and even in the tropics. So that begs the question of what is a dominant process that could give rise to such a relationship. We can think about the vertical mixing mechanism as one of them, where you have winds blowing over, say, warmer waters. And basically over warm SSTs, you sort of destabilize the overlying atmosphere and therefore can enhance momentum transfer to the surface and get faster winds. And the opposite in terms of inhibition of momentum from winds aloft to the surface due to the stability of the atmosphere. So over warmer waters, faster winds, colder waters, cooler winds, and you get this positive relationship at the mesoscales. If you extend this vertical mixing mechanism to 1 over a SST gradient, so you say you go from cool waters to warm waters, so slower winds on the cool side, faster winds on the warm side, this can induce a divergence here. And if you have the winds blowing along SST isotherms, you can induce sort of a curl. And these sort of processes can be proxied by the wind SST, by SST and wind speeds, but also by downwind SST gradients against the divergence, which is this case, and the crosswind SST gradients with the wind curls. So if we take a look at that, and also on its spatial scale dependencies, top left, you see based the relationship of wind stress divergence against downwind SST gradients based on the full fields. And on the top right is the smooth fields, and on the bottom is the high pass fields. So here in this case, instead, the full fields and the high pass fields actually look very, very similar, whereas it's not so the case for the large scale features. It is possible that this is the case that the full fields and the high pass field might look similar, mostly because these are the spatial derivatives when we take the downward SST gradients or the divergences, so that tends to almost act like a high pass filter sort of thing. Could be. Similarly, if we look at the crosswind SST gradients and the wind stress curl, you get this positive relationship, particularly over regions where you have lots of eddies and also fast winds. And you see this positive relationship that you can capture in the full fields as well as the high pass fields, but not necessarily for the large scale features. Then we also want to see current feedback metrics, and in this sense, look into surface current vorticity and curls, be it wind stress curl or wind curls. Just a little bit on the basics of how this might end up being the case. If you have background winds and you superimpose a anticyclonic eddy in the northern hemisphere, for instance, if you don't take into account the currents or this mesoscale eddy itself, then the wind stresses would just be of similar magnitudes across all of it, and you don't induce any curl. However, if you account for the mesoscale currents themselves, the ocean currents, then in places where they're in the same direction as that of the wind, that would mean lesser stress. And in regions where you have it in the opposite direction, that would be much more stress applied. And in this sense, this differentiation in the wind stresses can induce a curl. And the curl tends to be in the opposite direction of that of the vorticity or relative vorticity of the surface currents. If, however, you apply this over winds, so winds, and if the current and the winds are in the same direction, then you have less friction, and then you would have faster winds. And in places where it's opposite direction, lesser friction, so more friction, and therefore less strength in the winds or slower winds. And this would induce a curl, but then the wind curl would be of the same direction as that of your vorticity. So if we take a look at first the surface current vorticity against wind stress curl, so in this scenario where we explained that it's negative, the relationship, and true enough, if you compute that for the full fields as well as the high pass fields, they are in general negative. However, if we take a look at this smooth field, it's positive. I mean, this also sort of makes sense, right? You would want your, say, subtropical gyres or subpolar gyres in the ocean to be actually in the same direction as your large-scale wind systems. Okay, but say we look into vorticity against wind curl itself, where we said that they should be of the same sign. True enough, in the full fields and in the high pass fields, they are mostly red. And in the large scale, they are very red. I think this is consistent with the wind stress for the low pass filter or for the large scales, in that you would expect in large scales the winds and the wind stress itself to be in the same direction. Just to go a little bit deeper in terms of this between wind stress curl and wind curls themselves. So here it's based on the total fields, and you can see in regions where you have eddies, they tend to have lower correlation between them. And if you do the high pass, again, you can see clearly, and then in regions where you have high eddy activity, their relationship will be close to zero. Whereas for the large scale fields, in general, they have a high relationship between wind curls and wind stress curls. Please, I apologize for the ones around the boundaries. This is probably due to an artifact of the filtering that's used. I need to dig into that. But suffice to say that the mesoscales can induce these different types of wind versus stress curls. Last but not least, how this current feedback can affect wind work. Wind work is defined as the product of wind stress against ocean velocities. So if we take the case where you don't have the current feedback, then in this region here, where it's in the same direction, you get positive wind stress, which is, positive wind work, which is that winds are inputting energy into the ocean. And in regions where you have them in the opposite direction, this is negative wind work, so you can think about it as energy going from the ocean to the atmosphere. And so, but if they are equal, positive and negative, then in general, the wind work is 0. However, if you account for the eddies, then in this particular scenario, what's happening is that, again, your wind stresses have a gradient spatially, and therefore the positive wind work is smaller, whereas the negative wind work is much larger. So on average, or in its effect, what the mesoscale eddies are doing is that it has negative wind work, which is this term that they call eddy killing effect. And so you can see this clearly. This is wind work based on the total fields and the smooth fields. And in general, it's positive. So you have basically wind pumping energy into the ocean. But if you want to extract out, you do a high-pass filter and extract out the mesoscale eddy effect, we can see remnants of this negative wind work in areas where you have lots of eddy activities. So it's just to say that, yes, this eddy killing effect really only comes out when you resolve the eddies. But then here the question is, as you can see, between I used a 3-degree high-pass filter and 2-degree high-pass filter, and there's still a lot more red in this 3-degree versus this 2-degree. So I guess the one topic of discussion is that would the type or the scale of the spatial filter that's used be of importance, or something that we should discuss about when we're trying to do a lot of this extraction of the mesoscales. So yeah, it is the type or the length. By type of spatial filter, here I use a really simple, like a Gaussian filter, but like in work package 7, there's some consideration of using the GCM filters, which has a variable length scale for the filtering. And I think this would be a nice topic of discussion to think about that. Or also the spatial filters that we use for the eddy composites that Malcolm will talk about. It's the Bessel filter. So, I mean, this is crossover topic of us with work package 7. To see what types of spatial filters we might want to use. And these are just some thoughts of the discussion later on. But yeah, the idea of how do we quantify mesoscale eddies. So this leads back to the metrics and diagnostics that we're talking about. And Emma and Stella have very nicely put together and started a document for types of metrics and diagnostics we want to talk about. And this is meant for crosswork packages. Processes was some of the stuff that I've been discussing about, but there are lots more processes associated with eddies, as well as how to extract. So this is the part in the spatial filters. Yeah. Now I'll pass it over to you, Malcolm.
Well, so maybe we can pause there and kind of take any initial questions from.
Oh yes, that's right.
And then I'll carry on.
Right. Nikki.
Anyone?
Yeah, I put up my hand early on.
Oh, sorry, it doesn't. I can't see it on my screen. So go ahead. Yeah, go.
Thousands of questions. No, fantastic, Dian. I mean, I think the question you put up in terms of the methodology, I think, is going to be important. But let me first ask just an observation, which I'm puzzling over. Mm-hmm. Because there's a significant seasonal variability and also spatial differences in the way the atmosphere and the ocean are coupled. And at first sight, you would think, okay, for the different effects, let's say the coupling through thermodynamics, but also the different types of coupling that you have in terms of whether it's just the straightforward warm SST acceleration to when you think more about the gradients. The spatial pattern is for pretty much all of these processes slightly different. For example, one is really just has a sort of a strong subtropical, one is more seems to be governed by areas that has a high eddy activity. Others is more high latitude. Do we have at least a framework where you could say, oh, in those and those situations, I expect a stronger mesoscale coupling between the atmosphere and the ocean, and in those situations, I expect a lesser degree of this mesoscale ocean atmosphere interaction? Because I'm looking at these maps and I'm puzzled.
Okay. Let's see. I do imagine that a lot of them coincides in terms of like mid-latitudes and this high eddy activity regions, right? You have like in the Southern Ocean or in the Gulf Stream, in a lot of these western boundary currents. I tend to group them sort of together in a sense because these are SST frontal regions that are also associated with high eddy activity. This is indeed different from what from say when we see those coupling in the tropical regions like the TIW region. I still think it's a similar mechanism that is at work, but it's at a slightly different length scale. It's not necessarily related to eddies themselves, but the TIW is just the shape of it, and then that induces also this coupling. So the phenomenon itself or the processes involved in it are likely to be similar, but yeah, I mean, it's something that one needs to think about a little bit.
Yeah,
how to
where I'm
differentiate
going
them.
is of course I'm mostly an oceanographer, so I might show my ignorance maybe on the atmospheric side, but I do think that the atmospheric conditions matter probably quite well. I mean, what type of situation are we in the atmosphere? Is it more like are we in a storm situations? Are we in a high pressure sort of normal situation where it's more a steady wind? Or are we in a deep boundary layer and a shallow boundary layer? Do we have clouds or no clouds? I think there's probably going to be quite a bit of separation, not only from the perspective of what the ocean conditions are, but also in what way is the atmosphere conditioned to respond and interact with the ocean, or is it not? I have no sense of that.
No, I agree. So there are quite a bit of studies out there that especially talked about the wind conditions. So direction of the winds, but also the speed, which wind regime it's in. And so the coupling does have dependency on those factors too. With regards to clouds, I'm not as certain about that, but definitely atmospheric boundary layer conditions, possible separation between them would be good to take a look at to see what the implications are. I mean, like even in the tropics, when we do see this this sort of coupling, they tend to occur in the the TIW regions from the ocean perspective, but then that also coincides with the region of the stratocumulus, which you don't see. So except for the TIWs, you do still see some of this coupling over upwelling regions, even though the SST gradients are not as strong. So you're right in the sense that I think one could definitely, or we all could go definitely deeper into like having, say, concentrating on different types of conditions that might be favorable for such an RC coupling or not as favorable. I'm sorry. I'm thinking of flavor.
Thanks a lot. Yeah.
Sorry. All right. Yeah.
Super. Thanks.
Yep. Anne-Marie?
Sorry, go. Oh, yeah, go on, Anne-Marie.
Yeah, I mean, coming back to the ocean side of your question, Nikki, I was wondering whether there is some influence of the depth of the mixed layer, the seasonal variability of it, I mean. But perhaps that is something that you would not see in models, depending on the way they handle the penetration of the momentum, for example. I mean, in terms of the wind current coupling, I'm not sure how good are our models in representing the structure of the current near the surface.
Is this to Nikki or to me?
Well, both. I mean, I
Okay.
don't know whether you have looked at the different seasons. I mean, do you see very different patterns, for example, that would suggest that?
So the seasonality, there are differences because of the seasonality, but a lot of it tends to, or at least the ones that I've seen, they tend to associate with storms. So especially in the mid latitudes, during the winter time, you do see a much stronger coupling, and this relates to the wind speed regimes. So most of the studies in terms of these type of coupling tends to be more associated with wind speed regimes, rather than the base ocean condition. But I mean, I think you make a fair point, because like even in the tropical regions, the mixed layer for the ocean, mixed layer depth in the eastern tropical Pacific tends to be a lot shallower than the ones that we get, say, in the Southern Ocean. So I think these are different things to take a look into. And I guess I introduced these coupling coefficients. Well, I didn't introduce them. It's Renault had introduced them a long time back, but to use them as possible metrics for AC coupling. But I would really be open to thinking of other kind of ways that we might want to evaluate AC coupling to account for, say, ocean mixed layer depth or stratification in the mixed layer, against something in the atmosphere or at the surface itself too. I mean, I think you bring up a good point that we should go a bit beyond just the surface to surface interaction, and perhaps look into a little bit more into ocean mixed layer as well as atmospheric boundary layer. Yeah.
I mean, I don't have the answer to your question, and I mean, but we've done some interesting experiments in the past where we actually turned this coupling on and off, and then I think that probably would be a good way to look at some of these things. But I don't have the answer. Sorry, Malcolm, for interrupting.
No, I just had a quick question, Sigurlin, after I work in the regional sea coupling, and it's kind of related to Nikki's question around the cloud, the coupling between the cloud and the sea surface temperature. And we see that it's in the regional shelf region around the UK is quite dependent on the atmospheric conditions, and sometimes you can have a positive relationship between warmer SSTs will decrease low-level cloud cover, and sometimes it's opposite, depending on the regime you're in. And so I was wondering if just a simple metric around cloud cover SST could also be useful to look at globally. I don't know.
That's if we also trust our cloud distribution in the models.
Yeah, I mean, I guess the low-level cloud distribution.
We should
think that related to SST, otherwise,
right.
You have false correlations. But
no, agreed. I do think we need to include all. I mean, these are more like dynamical and thermodynamical quantities. It would really be nice to include a lot more, like the SST and cloud cover, or with precipitation, upward velocities, or even moisture transport or something like that. And in the ocean, it could also be like mean advective flux versus eddy advective fluxes, just to see what also controls the SST distribution. Since we think a lot of this coupling comes from SST or something, it would be nice to see what sets up the SST in the ocean. And that also feeds back to the cloud cover, I guess. Yeah.
Okay, since I didn't see any hands anyway, and I can't see any now, then it doesn't really mean anything. But if I'll just, I don't have too many slides, so yeah, right.
Excellent.
So yeah, so yes, I'm going to talk a little bit about the Lagrangian perspective. So this is using tracked eddies with the PY eddy tracker code that's used for the BESO observed eddies as well. So we've used that across the models. I think we've used slightly different settings of that tracker at the moment, so we might want to revisit that. And as Dian said, we might want to revisit how we filter the data, and we're currently regridding it to a quarter degree before tracking, which is what Aviso does. We may want to revisit that at some point as well. Most of the plots I have are with the Met Office data, but there is at least 7 years of track data from the ICON and AVI models, so I can add those as well. Just didn't get around to it. And I should say thank you to Dian and many others from EERIE, particularly for the code that was developed for the hackathon in November, because I've made lots of use of that. So this is just a plot of 20 years of eddy tracks. And for these, each of the eddy tracks is at least a year long. So it's the long eddy tracks. And the top is the model. So this is a 20-kilometer atmosphere, kind of 8-kilometer ocean. And the bottom is from the Aviso observations with the same criteria. Well, you can kind of look at that visually. I mean, visually, the model seems to have eddies kind of coming from the right places and kind of going to the right places. You can maybe see some regions where it's not perfect, or there's different balances between the cyclonic and anticyclonic, or the cyclonic being blue here and the anticyclonic in red. But as an overall measure, you'd say, oh, the model's doing okay. And I think if you plotted a lower resolution model, there would be, it would look a lot different to this. So it looks pretty good as a start. You perhaps note that the model in those 20 years has quite a lot more, kind of 1.5 times more eddies that last that long than the observations. And that comes out if you then do a PDF of the eddy lifetimes. So again, it's from the same 20 years of that same simulation. So on the top left curve here, the kind of lighter colors, the cyan and orange are the model for cyclonic and anticyclonic, and the deeper colors are the Aviso. And so you can see, so this is eddies by year over those 20 years. So you can see that the OBS actually have more eddies of short lifetime, but that kind of declines a bit more quickly than the model, and the model has more eddies at longer timescales. And that's where I'm thinking maybe that this eddy killing mechanism and this imbalance between the atmosphere and the ocean might be important, and it will be interesting to plot the other models on this same kind of figure to see whether there is some evidence that actually if you get the right atmosphere ocean resolution, that they interact in the right way, then you might change or kill the eddies kind of on the right kind of time scale. So that's something that I need to do. Here's a few more metrics, again, from the model and the observations. So on the top row here, the kind of cumulative distribution. So these are all now normalized to be between 0 and 1. The middle is the percent, and the bottom is the ratio between the cyclonic and anticyclonic eddies. So in terms of the amplitude, you can see that the observations, again, the darker colors, the amplitude is perhaps usually bigger in the observations than the model. And so you can see here indeed the peak in the lower amplitudes from the model eddies. In terms of the radius, so in terms of the kind of spatial size, the model is peaking at a slightly smaller, so the eddies are slightly smaller in the model compared to the observations. That's kind of interesting. Again, that will be interesting to look at the other models, because so we're both tracking on the quarter degree grid, so the grid's the same. But the observations, obviously, that it's not a global quarter degree data set that's being used. It's obviously tracks of the satellites, and then you have to interpolate. We await, I think, with bated breath. I think there's a new satellite due next year that might be a higher resolution sea surface height data set that might get us better information. And of course, we're regridding the models to a quarter degree here, so it's possible if we regridded it to 1/10 of a degree that the model eddies might get even smaller. But we don't kind of know whether what the observations are, because it's normally a 25-kilometer observational data set. So there's interesting questions there. The average speed, which is the speed round the swirl speed of the eddy rather than its translation speed. And so again, there's a bit of a difference here between the observations and the models. And then the shape error, this is how non-circular the eddy is, and with a bigger error is a bigger shape error. So the tracking that I did, at least, I cut the shape error off at about 70%. So the eddies can't be really, really non-circular. But again, it's interesting, and this maybe is, yeah, well, I don't know, that the observed distribution seems to be a bit more of a normal distribution than the model. So there's, again, plot more models, we might learn a bit more as to what that factor is. And then just today, like yesterday and today, I was then trying to do these plots. So this is the eddy density, again, over those same 20 years. So this is effectively for each 2x2 box here, I'm doing a histogram of that box for the 20 years of data. How many times do you find an eddy in this grid box? It's a very simple kind of track density. But again, this probably gives an interesting contrasting, or perhaps quantifies those tracks that I showed earlier. So for example, you can see perhaps in some regions, and maybe in South America and elsewhere, that there's kind of more concentration of track density than we see in the model. And indeed, we saw in the model that you don't get quite so many eddies in this region as you do in the observations. And again, so as we can do this with more models, we'll be able to see whether, is that a model difference? Is there a model resolution aspect to that to really be resolving the mesoscale features better? But so I think probably you can stare at that figure and kind of look at some quite interesting regions too. So then we, during the hackathon in November, we started playing around with the data and trying to do some composites. So we picked the Agulhas region. So these are Agulhas rings near South Africa. For the composites, again, they're not quite the same, but there's 7 years, using 7 years of data from ICON and IFS FISM, and 4 years from the NEMO data. I've used eddies that last at least 90 days. The other two last at least 60 days. And then so we then track the eddies, and then we composite the other variables along the track of the eddies, and then average up all of the composite. And so again, I won't kind of say very much, but you can see that there's, perhaps as you would hope for some of the variables, there's definite extrema on top of the Agulhas rings. So sea surface salinity, you can see a maximum kind of pretty much centered along the eddy in all 3 of the data sets. The SST, interestingly, in ICON, perhaps is a bit more asymmetric, whereas at least in the I think in the IFS FISM, again, the bullseye is more or less in the middle. Perhaps ditto the wind speed. There's definitely a precipitation signal in these 2 models as well. So you can see along the Agulhas rings, there's a peak in precipitation pretty much next to the eddy 2, and there's definitely a mixed layer depth signal as well, and the latent heat flux signal, which again is a bit different between the 2 different models. So there's more to look at, perhaps to do these in exactly the same ways, to see if we can understand some of those differences. Then there was a bit more detail in terms of looking at the kind of things that Dian was looking at, kind of relating things like the downwind ST gradients or the wind stress divergence to the precipitation, and then kind of looking at the Ekman pumping and the other aspects. I think I'd probably leave those for now. They're in the slides, but maybe I'll kind of stop there and invite any more questions from anyone. And you might want to shout, because it seems like I don't see any hands. Oh, there is a hand. Oh, no, that's a clapping hand. Thank you.
Nikki.
Just to break the ice here, When it comes to lifetime of eddies, I mean, it would be very interesting to have some ideas about uncertainties in the observational products, because I mean, having done that, not really myself, but my students and postdocs having done that, I mean, it's difficult from observations, and also because the Aviso product is generated from individual tracks from which you then determine a two-dimensional structure over time. Is there any way that we can get a sense of uncertainties in the observational products for those things? Does anybody know? So it's a question perhaps to the whole community rather than just to you, Malcolm.
Yeah, well, indeed, I definitely can't answer it. I mean, I think that there is this new satellite due in the next year or so that is meant to be, I think, higher, as I understand it, higher resolution. So, but I think we only have one satellite product right at the moment, so it's difficult to.
I guess it's also I was wondering if your eddies were too long-lived because because the way you're processing the satellite can't quite pick up eddies for a long enough time. I guess it's the frequency of tracks that will determine how long or how, the lifetime of your eddies.
Yes, yeah, maybe.
I don't know if it's a real overestimation from the model or there's also a bit of underestimation in the observations because the tracks are not.
Yes. Or maybe they get small. I don't know, they get smaller over time, and then maybe there's a cutoff that gets cut off more quickly in the observations than the model. But yeah. I mean, maybe if we can plot the other models, we'll maybe get a sense. I mean, it's not looking at observational uncertainty, but it would be interesting to see whether the observations are definitely one side of a distribution with the models all the other side, or whether the models go across the observations. Might tell us a little bit.
I think there's a question from Baba Tunda.
Yes, thank you, Malcolm. Please, can you shed more light about the relationship you found between the eddy and precipitation? Then the eddy you are plotting here, is it cyclonic or anticyclonic? I mean, the one you showed the composite.
So the composites all are Gullus rings. So I think that makes them anticyclonic, right?
Yes.
And then so actually, kind of what I cut off, I think, is and I think what Dian was talking about is the mechanism. So you can look at the SST gradient and the wind gradient, and I think the eddy can cause a convergence of the wind, which can then potentially cause precipitation. Dian is nodding, so I'm glad that I've more or less got that right. So I think this is the idea of at the mesoscale, the ocean eddy can force an impact on the atmosphere winds, which cause divergence and then potentially cause precipitation. I think that's the kind of general mechanism.
The co-location of it is sort of consistent with the idea that the ocean mesoscales can, like Malcolm said, produce the SST gradients that allows for wind convergence and therefore some upward motion in the atmosphere and then a rain out. That was the idea of it. And I think it's really nice because the thing is that typically that sort of like where the convergence is occurring and then you have upward motion and precipitation is canonically thought of as more of a tropical event and not necessarily in the mid-latitudes or beyond the tropics. But you could see evidence or signatures of possible forcing of similar concept, but beyond the tropics. Admittedly, it's not where the SST is located, but rather where the SST gradient is located. And I think that's the interesting part of it. Still not sure why it would be where the SST gradient is quite different from where the strongest SST anomalies are. That's something different. But in this case, that's the hypothesis that the precipitation imprint at least coincides with gradients of SST. Cool. I think you're still muted.
Oh, thank you. Yeah, it would be nice to also look at the kind of atmospheric feature that produces this kind of precipitation. So, I mean, in terms of the kind of looking at the structure, one would like to see what kind of atmospheric feature produces this precipitation, cutoff low, can it induce cutoff low, or mesoscale convective systems, and so on. So that will give more information about the interaction.
Thank you. I think after that will be Thomas.
Yeah, thank you very much, Malcolm. I've trying a little bit to understand these histograms where we look at properties of cyclone, sort of eddies, and and sort of how to interpret them, because I mean these are cyclones from different latitudes, and I guess there are good reasons to believe that there's the latitudinal dependence, and having perfect eddy characteristics at a certain latitude, but having them at the wrong number in the that may have an impact on these characteristics. So that makes it difficult to interpret, right?
Yeah. It's I was trying to get my head around earlier what the next step in my code is to do a latitudinal dependence for all of those characteristics. To write some code that can do the distribution, based on latitude as well. So that is the next step. I haven't quite wrapped my head around how I'm going to do that, but I do need to do that. And I guess maybe it's worth saying that. So obviously for the hackathon we had the GitHub site to do the code, and then I would certainly hope that as we develop code and stuff to do these analysis, that we can share those via the EERIE GitHub as well. So that, and indeed, so Dian pointed me to the tracks that are at DKRZ, and so I need to just remember how to run that code at DKRZ, and I can do these exact same plots, and then, as you say, do the latitudinal ones as well. So there's plenty to do.
I think Fraser is next.
Yes.
We can hear you.
Okay.
I
Nice.
see you now.
Sorry. Okay, good. I was interested in this kind of eddy-induced Ekman pumping and suction kind of slide. So one of the things which I've been looking at is VH traces in the icon model, and looking at sort of the implication, or looking at how we can look at passive trace uptake and I guess release from the ocean that way. Do you think the eddy-induced Ekman transport, could that be important for things such as, or could that lead to biases in terms of, I guess, things like the uptake of carbon and CFCs at the surface? Is this pumping strong enough to do that, or is it quite weak? Sorry, yeah.
Okay.
That's a good question.
It's a good question. I think we need to, so I have not quantified by how much of a difference this would really make. It was more of to see that, for instance, things like in anticyclones, in general, we would have assumed in anticyclones that you have a downwelling associated with anticyclones. But this eddy-induced Ekman pumping actually induces upwelling within anticyclones. So perhaps by including such processes, then the uptake that we might have considered due to presence of anticyclones, for instance, is maybe diminished, but by how much, I do not know yet. I mean, something that we could ponder about how to quantify the effects of this. I mean, I sort of, I did make sort of a figure with regards to like just total distribution of these of this Ekman-induced, eddy-induced Ekman pumping. And they don't look as different from just Ekman pumping itself from the wind stress curl. So I don't envision it to be as big of an impact, but it's not yet quantified. So I think we need to look into it. So,
Okay. Thank you.
no problem. Anna, I believe, has a question.
Hi, Malcolm. Yeah, this question is from Malcolm about the eddies. I was just going to ask, were the same parameters used for both the altimetry eddy tracking and the model ones? Oh.
For the tracking that I did, then I believe so. Yeah, so I did talk to the person who's involved in the Aviso tracking, and so I think the parameters that I've used are the same as they use for the tracking. Yes. So I'm just using the eddy data set that Aviso produced because yes, I think I'm using the same tracking parameters. I think perhaps for some of the other groups where they're slightly different. So, but then we're also thinking about how to do the initial filtering before we do the tracking. So we may want to do all of this again in a more consistent way. But yeah, as far as I know, the model is tracked. Yeah. Yeah.
Because definitely you can tune how you can follow the eddies, and if one eddy disappears at a given point in time, you may or may not be able to recover it on the next model time step or a visual. The other question I had was related to depth. So you have shown these results for surface eddies. If you are going to do a comparison with the other models, I know you cannot compare with observations, but it would be nice to see how the models compare at different depths.
Yeah.
So go on, Dian.
No, okay. We have been discussing about that. It is definitely something we wanted to take as a further step in terms of not just looking at the surface, but indeed to see how deep it goes. Some of the questions that came to mind really quickly was how, you know, at deeper depths, how then do you define an eddy boundary? You know, is it just like the anomalies 2Ds again, and you filter out the rest? And is that what we're going to look at in terms? Do you use the thermodynamic? Do you use a dynamic property as a boundary of the eddies in the subsurface? But there are lots of studies out there that look into the 3D structure, so we probably would have to go through and figure out which ones we might want to use. Yeah, but yes, definitely a consideration. The 3D structure would be really interesting. I mean, that was my thought earlier when I was even doing this for just the precipitation and then looking into the atmosphere. Then it's like looking into the ocean would be extremely interesting to see what's going on. But then looking,
So I just say, so some of the modeling groups, not me, have run a few years and got daily 3D output from the ocean. I have not, but I've got 5 or 6 levels, kind of 50, 100, 200, blah, 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 down to 1,500 meters. So potentially we can do some 3D stuff, as Dian said. If we can figure out how to do it, then we do have information at this group levels down to 1,500 meters that we can look at some of the 3D structure.
Good. That would be really interesting to see. Thank you.
Welcome.
Thanks.
Also, just the comments that you mentioned with regards to the time stepping of the splitting and then merging back of missing data in between. I think within PI-eddy tracker itself, the program we use, we could specify how many days you miss the eddy and consider that it's still part of that eddy as you track it along. But even those things are parameters that maybe we want to discuss in terms of keeping it consistent for model comparisons.
Yeah, thank you.
I guess we are 3 minutes over time. But if there's no other questions, going once, twice. Okay, Well, thank you all for joining in. I guess we will definitely see each other soon if you're attending the EERIE medley session. And if not, latest next month with the science hour from Work Package 6, I believe. Right? Yeah. Thanks everyone for being
Thanks,
here.
Dian. Thanks, everyone.
Thanks, Dian. Thanks, Malcolm. Thanks, everyone.